One of the most interesting physics concepts is the inverse square law. And although this video won't explain the inverse square law, it will explain this funky looking graph. Why is there a circle here? Why are there these random axes just drawn on the surface? And moreover, why is this line here looking so weird? And why is it just random curve here? And what is going on here? Well, this is the graph of this equation. This is the graph of f of g is equal to 1 over d squared. So this is showing the force of gravity at different distances away from Earth. So if I say that this right here is Earth, this is showing the different forces of gravity at different distances from the Earth. So this right here is at the center, although it doesn't look like this. This is the center of the Earth. This is 5 times the radius of the Earth. So this is the radius of the Earth is at this line. This line is tangential to the surface of the Earth. So this is the radius of the Earth. This is 2 times the radius of the Earth, 3 times the radius of the Earth, 4 times, 5 times, and it'll go on all the way up until essentially infinity. This right here, if you don't know about exponential curves, this is an exponential curve. This is that's the reason, because this is d squared over here. So if we look back at this equation, we see that this is d squared. So that's why it curves off like this. It'll never. The interesting thing about this curve is that it'll never dip below 0. It's always going to stay just above 0. The force of gravity might become 1 times 10 raised to the power of negative infinity, but it'll never cross the 0 axis. So that's why this graph is like this. Now, why is it getting closer? You would think that, okay, so if the force of gravity is getting less and less as you get farther away, because obviously d is increasing, well, then that doesn't make sense, because let's say d is equal to 1/2, then we should do f of g is equal to 1 over 1/2 squared, which is essentially f of g is equal to 4. So then why, if f of g, why is it not 4 here? At this point, why is it, in fact, much less than if you're at the surface of the Earth? Well, if we take a look here, if I were to draw a picture of the Earth here. This is the Earth, a smaller version of this. If we were to take a look at this, we could see, I'm going to draw 3 zones. I'm going to divide this up into 3 zones. So there's 1 zone, that's 1, there's 2 zones, actually, oh, you know what, actually, let me try this again. Let's try this again. Let's say that's 1 zone, and then we'll make the next zone blue, just to see here. 1, 2, and then the third zone's whatever's inside this blue area. Now, if we took a look at this, imagine that the areas inside each are the amount of mass pulling on you. Well, if we're at the surface, anything inside the green area is pulling on your body. You have all of this, all the stuff inside the red, all of the stuff inside the blue is pulling on your body. That's a lot of matter that's pulling you down. That explains why at the surface of the Earth there's the greatest amount of force of gravity. But if you go to the red zone, as we progress down the red zone, all we have is whatever's in the red zone and whatever's in the blue zone. We don't have whatever's outside on the green zone. In fact, that's actually pulling us back up to the surface of the Earth. It's pulling us away from the center. So if we look at if we go even further and look at the blue zone, we actually now have most of our forces being pulled this way. Some of it's being pulled down this way, some over here, because remember, this is a circle and we have mass pulling us in all directions. So the F net at the center, F net is 0. If F net is 0, then our weight cannot possibly be 0. So we cannot possibly have any weight. So that's why at this point here it's 0. And as you get farther away, as we would expect, if the distance is 2 times, then 2 raised to the power of 2 is 4. So that force of gravity is only 1/4 of if you're at the surface of the Earth. So if you're thinking that you're going to get crushed under the weight of the Earth if you go closer to the center because you weigh so much, that's not exactly true. Although there is lots of things pushing, there is lots of force, which is exactly why if you go deep underwater, you'll need a submersible because there is a lot of weight. However, you do not weigh anything at the center of the Earth. So if you were to have so in that sense, if you were to dig a tunnel, that went straight from pole to pole, what would happen? And if you dropped a ball from this top of the part of the tunnel, it would essentially go through, and it would speed up at a decreasing rate. Right here, it'd be 9.8. Right here, it might be a little bit lower than 9.8, maybe 7.6. Then it would keep going down until at this point here, at the very center, you're not accelerating. However, you're still moving. So that's why you can power through the center still. And at that point, you're decelerating. And so when you get back up to the top, you're going at the same speed as you left with. So that's a very interesting concept here. Also, if you were to dig a tunnel straight through, let's say this is one side, New York to Los Angeles, or let's say this is even Los Angeles, even shorter, let's say that's Los Angeles to Phoenix, we would still take the same amount of time to travel, approximately 40 minutes, if we were to travel straight to the center of the Earth. That's because the pull of gravity is now not at directly down in your direction of motion. It is now slightly opposing your direction of motion, or not exactly in line with your direction of motion. So that would be why it takes you, still, if you were to dig a tunnel straight from Los Angeles to New York, you would be able to essentially travel in 40 minutes rather than 5 hours.